In this session, we are going to look at an important interview question based on bitwise manipulations. Given a number n, count the number of ones in its binary representation. Number of ones is nothing but number of set bits in the given number. This is one of the commonly asked interview question in the service-oriented companies, and we call them as type 3 companies. For example, given number is n, and in its binary representation, let us say number of bits in the given binary representation depends on the mission configuration. For simplicity, we are taking 8 bits, but actual number of bits, it depends on the mission configuration. For this number of set bits are 4. First one, second one, third one, fourth one. So number of ones in the given binary representation for this number is 4. For example, if you make it 1, it will be 5. Number of set bits in the binary representation of this number. For this problem, we have multiple solutions. And in this discussion, we are going to look at 4 of them. First one is with bitwise AND operator. With modulo operator. With the toggling approach. And with group processing. Now let us see one by one with bitwise AND. Given number is, consider another number 1 and in its binary representation all zeros followed by 1. If we perform bitwise AND between these two, overall output will be since the least significant bit of the given number is 1, that's why we are getting the output as 1. What is the observation here? Let us assume we have a counter C initialized with 0. Here the observation is we are processing the least significant bit of the given number. We are ignoring all the remaining bits of the given number. And if it is 0, output is 0. If it is 1, output will be 1. What is the observation? If it is 0, we are getting as 0. If it is 1, we are getting the output as 1. It means, since you are performing the bitwise AND between the given number and a 1, that indicates whether the least significant bit is 0 or 1, whether that is a set bit or not. If you are getting the output as 1 means the corresponding least significant bit of the given number is 1. So we can increment the counter. So if you perform bitwise AND between the given number and 1, if the output is 1, that indicates this bit is 1. That's why we are incrementing the counter. We have seen one state bit so far. So how do we process the remaining bits? We are done with the processing of the least significant bit. How do we process the remaining bits? For that, we can shift the given number by 1 to right. So we will perform one right shift operation. So what will be the output after first shift operation? So this one will go away. What should be this value? Since we assume the given number is unsigned integer, we will add 0 here. If it is signed number and if it is in 2's complement representation, we need to be little careful. For simplicity, we assume the given number is unsigned integer. That's why we are adding 0. Again, apply the bitwise AND between the current value of this one and 1. Again, we got 1. Increment the counter. Again, perform right shift to given number. That means here we are crossing the least significant bit, that is nothing but the second bit of the given number. That way we keep crossing all the bits of the given number. When do we stop? Since we are adding 0 to the most significant bit every iteration, after crossing all the bits of the given number, the n value will be 0 because we are adding 0 in every iteration. So we can stop the crossing as soon as n becomes 0, right? So at the end we can return whatever is the count value, that is nothing but C value. How do we code this one? Since we assume the given number is unsigned integer, I'm declaring right away. I'm just thinking in terms of C and C++. You can similarly find for other programming languages as well. And another counter C initialized with 0. As I said, like while n greater than 0, or you can put it as n greater than 0. In each iteration, if you are performing bitwise and between n given number and 1, if that is 1, you can increment the counter. If that is 0, we don't have to do anything. You can ignore the C value, whatever the current value. And in each iteration, we are performing the right shift for bind. So this is the process. And at the end, we can return C. So since we are incrementing the C value in each iteration, whenever we see the output as 1. So that way we can keep track of how many ones are there in the given binary number. So what is the complexity of this code? For example, given binary number is 1, all zeros, whatever. Whether remaining bits are all zeros or ones, it doesn't matter. We are crossing all the bits of the given number until the given number becomes 0. So the worst case complexity, nothing but we are crossing all the bits of the given number. For example, let us consider other way. If n is equal to, in this case, after first iteration, n value will become 0. That means we are stopping after the first iteration itself. That's why in the worst case, if we add 1 here, we are crossing all the bits of the given number. So overall complexity of this code is nothing but number of bits in the given number. So in this case, we assume that is the mission representation of the binary number is 8 bits. In other mission configuration, it can be n, whatever the value, depends upon the mission configuration. Since we don't know the number of bits, assume number of bits of the given number is b. That's why the complexity of this code is order of b. And since we are assuming worst case complexity, that means the upper bound, number of bits that we are processing for this given number. Now let us see the second one with modulo operator. The idea behind this solution is on pretty much similar lines with how do we convert the decimal number to binary. To convert decimal number to binary, we keep dividing it 2, and if the percentage, the modulo 2 is 0, we'll add 0 to the output. If it is 1, we'll add 1 to the output. That way we convert the decimal number to binary. On the similar lines, for a given number n, if the modulo 2 is equal to 0, that means the least significant bit of the given number is 0. If it is 1, that is nothing but least significant bit of the given number is 1. That way we can keep track of how many ones we have seen so far with a counter. So how do you write this code? Again, since we assumed given number is unsigned and another counter C initialized with 0, while n, again you can put it this one as well. That means we have seen 1. The least significant bit is 1. So the main logic is this one. And in each iteration we are dividing the number by 2. Either you can divide the number by 2 or you can perform right shift operation. Both are okay. What is the complexity of this code? How many times you are executing this while loop? If all of them are ones or ones followed by zeros, the complexity of this code is also very much similar to the previous one with Bitwise n. Because we are dividing the value by 2 every time, so it's nothing but, for example, for simplicity, if n is equal to 8, after the first iteration it becomes 4. That means it's indirectly nothing but we are shifting the number by 1. So that's why we are adding 0. In the next iteration, it will be 0, 2. In the next iteration, it will be 0. So to simulate the right shift operation, we are dividing by 2. So the complexity of this one is also number of bits in the given number. Remember, whether the bit is 0 or 1, we are always processing. That is the main observation for these two solutions. That means whether the corresponding current bit is 0 or 1, we are always processing the while loop. Because of that, the complexity of the both the codes we are getting is the order of b, that is nothing but number of bits in the given number. Okay. Now let us see toggling approach, third one. And I said like with these two, when the bit is 0 or 1, we are always processing the bit. Now with the toggling approach, we process the bits equal to the number of ones in the given number. If the given binary representation has 5 bits, that means 5 set bits, we will execute the while loop only for 5 times. If it has 10 ones, we will execute for 10 times. If it has 1, that means only one set bit, we will execute the while loop only for once. If it is 0, we will not execute the while loop at all. That is the idea behind toggling approach. So the idea here is, the given number is, so what is n minus 1? That means binary representation of n minus 1. This is 7, so we can make it as 6. I just usually look at the last 4 bits or 3 bits, and based on their value, I reduce it by 1. That's why since it is 7, I am making it as 6. So that's the value n minus 1. So what is the output of applying bitwise AND operator between n and n minus 1? In the next iteration, let us make this as n. Keep observing what we are doing. So again, in this case, since n and n minus 1 become n, so what is n minus 1? Since this is 6, I will make it as 5. Again, what is n and n minus 1? This n between these two. And in the next iteration, this becomes n. So what is n minus 1? Since this is 4, I make it as 3. And what is n and n minus 1? In the next iteration, it will become n. So what is n minus 1? Do you agree? What is the observation here? Why we are going for n and n minus 1? What is the advantage of that? If you carefully observe, n and n minus 1 always toggles the rightmost set bit. Here the rightmost set bit is this one. Since we are actually considering, since we are considering n minus 1, the output is this one. So the overall n and n minus 1, remaining all bits are same except the rightmost bit. You can observe, compare these two. In the next iteration, we have made this as n. And n minus 1 is, this is 6, we have made it as 5. So in this case, the rightmost set bit is this one. What is the n and n minus 1 of this one? You can see that has become 0. It always toggles the rightmost set bit. That way it keeps going. In the next iteration, we have made this as n. And n minus 1 is this one. What is n and n minus 1? Since the rightmost set bit is this one, that will become 0. Clear? So n and n minus 1 toggles the rightmost set bit always. Now, let us consider another example so that you will get clarity. For example, n is equal to just this much. What is n minus 1? Since this is 2, I will add 1. What is n and n minus 1? As I said, like the rightmost set bit is this one, it toggles that. Remaining all bits still. Do you agree? Even if you perform n and n minus 1, it will be same. It just toggles the rightmost set bit. In the next iteration, so we are assigning that to n. At this point, what is n minus 1? This is 8. I will make it as 7. What is n and n minus 1? Zeros. What is observation? Just after the second iteration, the n value has become 0. Since the n and n minus 1 is toggling the rightmost bit every time, the number of times we are executing the loop or whatever is equal to the number of set bits in the given number. So the number of iterations that we'll be doing is equal to the number of set bits, not the number of bits. So in this case, we have 2 set bits. That's why we have executed only for 2 times. If it is 0, we'll be executing only for once. So the advantage of this approach is, in the first approach, second approach, we have executed the while loop equal to the number of bits in the given number. But in this case, we are executing the loop or iterations, the number of iterations equal to the number of set bits, not the number of bits. How do we code this one? If you carefully observe, during the iterations, we never checked whether the value is 0, 1 or not. Blindly we are checking. Every time we are just performing n and n minus 1 and assign it to n. So int n, you can assume a similar approach. Unsigned number, another counter, again while n or n greater than 0 again. This is the simplest code of all. Blindly we are applying the operation n and n minus 1 and assigning it to n in each iteration and incrementing the counter every iteration. So in the first iteration, if the value itself is 0, will not come inside and the counter will be 0. If it is non-zero, we are coming inside, and with this operation, we are the rightmost set bit will be 0 and incrementing the counter. That means how many times we are processing that one, how many times we are clearing the rightmost set bits, equal to the number of iterations, that is nothing but number of set bits in the given number. So what is the complexity? Order of set bits. How many ones actually in the given binary representation? That is equal to the number of iterations. Now let us see the last one with group processing. You can say pre-processing as well. With group pre-processing. So in the first three approaches, we have processed one bit at a time. We process one bit at a time. We process number of bits equal to the number of set bits in the given number. But still we are processing one bit at a time. But in the case of fourth one, with group processing, we will be processing multiple bits. So idea here is, for example, this is the given binary number. Instead of processing one bit, we will be processing a group of bits. Let us say 4. It does not matter whether you process 4 bits at a time, 2 bits at a time, 3 bits at a time. It's up to your logic. Let us assume you are processing 4 bits at a time. So if you are processing 4 bits at a time, how many set bits in the 4 bits? In this case 3 and in this case 2. By looking 4 bits at a time, we have to see how many set bits are in the 4 bits. How do you find that? So for that we will use the concept of pre-processing. The idea behind pre-processing is pretty much similar to how we implement next prime numbers. As you know, finding the next prime number is complicated operation. For all such time-consuming operations like finding 100th Fibonacci number, 100th prime number, 200th prime number, we do some pre-processing, and depending upon the algorithm, we pre-compute the values and put it into table. Whenever required, we directly take it from the table instead of recalculating on the fly, which are complicated operations. This solution is also based upon the pre-processing. So instead of checking each bit at a time, we'll be checking 4 bits at a time, and we do some pre-processing for 4 bits actually. So for 4 bits out of zeros and ones, how many total possibilities are there? 16, right? So for 4 bits we have total 16 possibilities. Out of these 16 possibilities, let us see how many set bits in each of the sets. 0 set bits, 1, 1, 2 set bits, 1 set bit, 2, 2, 3, 1. As I said, like we are pre-processing the 4 bits actual possibilities, all possibilities, and putting into table. And by looking at input, we consider 4 bits, and for each of the 4 bits, we directly go to the table. Since the value is 7, we go to 7, see how many bits are set bits. So we see actually, we have 3. So that's why we got 3. So we add 3 to the counter directly instead of one bit processing at a time. And once we process the 4 bits, we'll be shifting the bits by 4 actually to the right. So in the first case, we have shifted the given number by 1 to the right, right? So we performed 1 right shift operation. So instead of 1 right shift operation, we'll be performing 4 right shift operations. Okay? How do we code this one? How do we code this solution? We initialize the array with the values whatever we see here. 0, 1, 1, 2. So this is the initialization of pre-processing of the 4 bits. And the given number, counter initially 0. . while n similar to or n greater than 0. Once we fill the table, we can remove all this one. Observe carefully. Whatever the current value of C, yes, here we are performing a bitwise AND between the given number and 0f. What does that mean? So in the first case we have seen, right, we have performed the bitwise AND between n and 1. That means all zeros followed by 1. So in this case, since we are performing bitwise AND between 0x and f, that means hexadecimal representation of 0f, that is nothing but 4 zeros followed by 1's. And whatever the given value. The given number is 0, 1. See here, this indicates that we are considering the least 4 bits. We are considering the least 4 bits. So if you perform bitwise AND between the given number and least 4 bits of the number, we will get the corresponding table entry. So what is the value here? You see, 7. And that we are indexing it to the table T of 7. Whatever value we have already seen, that is nothing but 3. So that we are adding it to the counter. And we are shifting the corresponding current value of n to 4 bits actually to the right. That means 4 right shift operations. Again, in the next iteration, so these 4 bits are going away and we'll add 4 zeros to the left, that is nothing but most significant bits, followed by 0, 1, 0, 1. Again, 4 zeros followed by, this is nothing but 0f. This is nothing but. Again, what is the output here? We are directly going to 5 of table. 0, 1, 2, 3, 4, 5. So that way we are getting 2 here. That value we are adding it to the table. From the table we are adding it to the count. So the idea behind this approach is, instead of processing single bit at a time, we are processing multiple bits, that is 4 bits at a time. And how are we calculating the values? That means how many set bits are there in the corresponding 4 bits? By using the pre-processed table. So what is the complexity of this code? Let us say the number of bits are b. And depending upon the pre-processing entries, since we process the 4 bits at a time, so b by 4. So we have seen 4 solutions. We have got order of b, order of b, order of number of set bits, and order of b by 4.